plus by omega L over 2, right? And then the last term don't have, so plus by 7 over 128 omega L. The whole term will be equal to 0, right? The whole term is equal because dm by dx is equal to v as a function of x, right? So when the shear force is equal to 0, right? So i.e. shear force is equal to 0, bending moment will be equal at its max. Yes or no? Okay, just to make you guys recall, probably you guys have learned this in 2P04, but I want you to recall. So x, omega x is equal to, so half plus by 7 over is equal to 31 over 128. Omega L. So x is equal to 71 over 128 omega. Okay, or L. So at this position, right? At this position where we will get your what? Mmax. Okay. So Mmax is method of substitution. I will not do in detail. You just have to trust me. 71 over 128 L. Okay. So it will be equal to 945 over by 32768 omega L squared. So this will be equal to 0.0288 omega L squared. Okay. So I'm going to quickly sketch this out. Okay, we are going to quickly. So 71 over 128. This is equal to 0.55 46 or 47 L. Okay, so I'm going to quickly sketch this out. Okay, so this is the last part. So we have our x-axis, right? So this is 0.5 L. 1, 2, 3, 4 L. This is our x-distance. Then this is our moment. Right. So our moment, it will be a function of omega L squared, right? So this is 0.01, 0.02, 0.03, right? So when x is equal to 0, 1 point is here, and then when x is equal to 0.5 L, right, we calculated it is equal to what? It is equal to, I know I'm also having a headache, 0.02734, okay? 0.02734, so 0.02734, okay? So this point is our 0.02734 point. Am I right? 0.02734 point. Okay, so it's going to be a straight line. We know that based on the function, right? So then you're going to see a peak at 0.55, okay? So you're going to see a peak at 0.55. So when in your exam, when you do this, you have to write down, okay? So this is going to be 0.5547 L. Okay, so I missed. So the first point is 0.5 L. Okay, and then the magnitude will be equal to 0.0288 omega L squared. Okay, so this is the peak, and then when it finish off at 0.07, so this is my 0.01, 2, 3, 4, 5, 6, 7, and minus 0.08. All right, you'll finish off 0.0703. Okay, so this is your last point, L, and this is equal to minus 0.0 703. Okay, is it 703? 0.0703. I'm right. Okay. So from here, you sketch your curve. Okay, it's not a straight line, it's a curve now. So this is how your shear force diagram look like. Okay, so that's the power of the elastic curve. Okay, you can solve any structures, statically indeterminate structures. So one thing I want you to take note is over here, when using elastic curve, you can also use what? You can also use positive bending moment to find the bending moment equation. You don't need to use the integration method, okay, for this case, right? And I did not choose to use integration method because I know all my distances. Okay, if the distance of the equivalent load is not known, then you have to use what? The integration method.
Eugene, could you go over like at a very high level how you approach this problem again, just like very generally, how you broke it down?
So the first thing to identify is to see that's a good question, by the way. So you have to see, can you find the position of the can you find the position of the equivalent load, right? If you can find, you can use the positive bending moment. Like down here, you can start applying positive bending moment and positive shear. If you can't, you have to use the integration method. Okay, so that is the first thing. Then after that, you form your bending moment equation, right? So you form your bending moment equation. You see the solution procedure. You form your this is critical. Okay. So you form your what? You form your bending moment equation, right? Then you go into your positive shear. Then you go to the elastic curve. So you just put in EI is equal to d squared y over dx squared. Okay. Right. Then you integrate again and you integrate again. You have to be very cautious about your what? Boundary condition. Like for this case, you have to be very cautious about the boundary condition. Initially, we only know our boundary condition. We only know this boundary condition, this boundary condition, and this boundary condition. And then later we realize, hey, it's not enough. Then you at point C, we realize that the equations are equivalent when x is equal to what? L over 2. Okay. The rest is just very simple, tedious math. I'll tell you that. Right? The math down here, like I think if you finish your first year math or your second year math, you are able to solve it. The math is not difficult. Okay. It's the interpolation of a physical system, right? To get your what? Boundary condition and solving it. That's where the issue is. Okay. Does that answer your question?
Yes.
Yeah, so I think it's good that I don't need to write it down. You can repeat the last few minutes of this lecture, okay, and listen it to it well, okay? Any other questions before I let you guys go? I know I'm overdue. I do apologize. Any other questions, please? No? Okay, if that's the case, I'll see you guys. Oh, by the way, I've posted the homework already, and I'm going to post the quiz today, and the due date is on Friday. Okay, I'll see you guys then. Thank you.
Eugene.
Yes.
So with these questions, is it such quick